Okay, so hi, welcome. Today we want to start talking about Q value. So we've covered enough that you should be able to do Q values now. Okay, so this is number 11. Going to talk about Q values. So what have we covered last time? Okay, so I just want to emphasize 2 points. Okay, mass excess, it's a measure of how tightly a nucleus is bound with respect to carbon 12. Okay, so the as we recall the last video, when we talk about binding energy per nucleon, and then last two videos talk about binding energy per nucleon. We sort of discussing how uh, the tighter the nucleus is bound, the more energy is released when you fuse them together. So binding energy per nucleon, okay, more will be released, and the tightest bound nucleons are somewhere around iron and nickel. Okay, let me just do this. Yeah, somewhere around iron, 56. But for light nuclei, it's not as tightly bound, okay, as let's say iron. Okay, and mass excess uses this carbon 12 as the benchmark. So you can see anything below carbon 12 will usually have a positive mass excess. Means to say it will weigh heavier on average per nucleon. Okay, so there are 12 particles here, but if you divide it by 12, that's the average mass per nucleon of carbon 12. You'll see that all the light elements here, they have a less binding energy per nucleon, means to say they are on average heavier because they're not fused so tightly yet. They have not released that energy. Same for uranium right here. It's about, okay, I can't really see here, but it looks like it's on par with carbon 12. So it's a decently tightly bound nucleus, but not as tight as iron 56, krypton, or tin. So these are very stable nuclei. In terms of if we talk about binding energy anyway. Okay, of course, stability is not just talking about binding energy per nucleon. You got to talk about the proton and neutron balance as well. If there are too many protons or too many neutrons, chances are beta decay will happen. But anyway, let's talk more about why we like to talk so much about mass excess. Okay, or binding energy. Okay, we want to discuss them in context of nuclear reactions. For example, nuclear fusion and nuclear fission. So why we bother about them is because we use fusion and fission processes to release energy. Okay, majority of if not all the commercial power plants now are using fission. Okay, fusion, you will only see it more often in nuclear weapons at this present moment. Of course, there are experiments to try and harness fusion energy commercially, but at least for now, magnetically confined fusion is non-commercial. It's very difficult to make reality. Okay, some people are optimistic. For me, I look at what's already available, and that's fission, because I'm engineer by training, and so I kind of am biased in that sense. But if you want to talk about pragmatism, fission is there, it's proven. Okay, in terms of commercially ready energy. So let's calculate energy released. Okay, we bother about, bother about binding energy, mass excess, and mass defect. Okay, so mass excess is how tightly bound it is with respect to carbon 12. Mass defect is, well, how tightly bound it is, how much energy you release it describes the idea of how much energy you release by combining individual protons and neutrons together. So there are different things here. But we care about this because you want to calculate energy release in fusion and fission processes. I mean, that's the main reason why we are interested in this for nuclear engineering or nuclear energy. Interested in how much energy is released in fusion or fission process. Okay, so what do you call the energy release in a nuclear reaction? Okay, we call them Q value. Okay, Q is usually the symbol used for heat energy in thermodynamics. Okay, if you talk about the first law, the heat supplied to a system plus the work done on the system equals to the change in the heat energy or internal energy of the system. This is the first law of thermodynamics. Of course, sometimes you'll see a minus sign, but the law is basically one of conservation of energy. So if you see a minus sign there, it means it's the work extracted out of the system. So there shouldn't be too much of a discrepancy there. Just be careful what W means. Is it work done on the system or work done by the system? But anyway, Q is usually heat supplied or heat loss from the system. And in this case, this system is the system of reacting particles. Okay, there's no work done here, so there is nothing here. You just have a change in internal energy, or internal energy could be heat, heat energy, potential energy, and nuclear energy is technically one of these forms of internal energy. Okay, in this context. Okay, so we like to call this the Q value. Okay, so Q value is the energy released in a nuclear reaction. Okay, is energy released in nuclear reaction. Okay, so there's nothing too technically new. It's basically similar to what we have done before. We can use mass excess or mass defect to calculate the energy release in this reaction. So the concept, okay, if you were to use fusion as an example, you have a deuterium atom plus a tritium atom. This is hydrogen 2, hydrogen with 1 proton. Okay, hydrogen 1 proton, 1 neutron. That's deuterium. Hydrogen with 1 proton and 2 neutrons, that's tritium. This will normally react to form helium-4, which is an alpha particle. 2 protons, 2 neutrons, and then a lone neutron here. Okay, so this is fusion process. Okay, a lot of the commercial reactors, they like to use this process. This is not what happens in the sun. Okay, in the sun there will not be this. You will use, it's like likely something called the proton-proton chain, if I remember correctly. But yeah, it's the proton-proton chain where you fuse protons together, like so. Okay, you fuse the protons together, and you get a deuterium atom. Okay, so one of these so-called undergoes positron emission, electron emission. Sorry, no, positron. It has to get the positive charge out of, yeah, it's a positron emission. Yeah, so you have E plus. Okay, so if you talk about the hydrogen nuclei themselves, if this is a plus and this is a plus, the positron comes out. But of course, this positron will actually this one is an antimatter thing. Okay, positron is an antimatter. It will usually combine with an electron to give you 2 gamma rays. Okay, that's something we deal with more in the Feynman diagrams, but just ignore this for now. This is what usually happens. Okay, in the sun, there's a proton-proton chain where you have lots of hydrogen around, and they'll just keep knocking into each other. And normally, okay, the correct term is quantum tunneling, but uh, if I remember correctly, that's the process. But I just want the main thing I want to highlight is that this is what happens in the sun, not this. Okay, this is what we try to do on Earth. Okay, because it's a lot more bang for buck. Okay, that's what I'm trying to say. Okay, so let's calculate the Q value of this. Okay, we can use the wallet cards as before. I'm not going to refer to them in the PDF. I'll just give you the individual what do you call that, nuclei, or the individual atoms and their respective binding energy. So this hydrogen here has, or rather deuterium here has a mass excess of this much, 13.136 MeV. Tritium 14.950. So see, this is actually slightly more loosely bound. Yeah, it's loosely bound. Okay, helium is very tightly bound compared to carbon 12, so it's less mass excess. Neutron is 8.071. So you can see that what do you call that? Hydrogen and tritium, they're not very tightly bound in general. Okay, but that gives us the opportunity to have them release energy through fusion. So how do we calculate the Q value? Okay, how do we calculate the energy release? Okay, so we look at the reactants. These are the reactants, which is the tritium and deuterium. So deuterium and tritium. So these are the reactants. Okay, we look at the mass excess of them. That's the before. This is the after. So we just do simple addition in the following manner. So this is the reactant side. Okay, let's take the mass excess, 13.136 MeV plus 14.950. Okay, products. That is the helium here and the helium and the neutron. So 2.425 plus 8.071. Okay, so this is how you calculate the energy released in a nuclear reaction. If we have the mass excess, it's very simple addition, subtraction right here. So use those wallet cards. Okay, I'm not going to do the mass defect part because again, my emphasis is more on concept rather than the math, but a lot of course work will have to do with it. Okay, at least for now, I will not do it. Maybe in another video. So to calculate the Q value, you just take the difference between the reactants, between the mass excess of the reactants and the products. So you take the mass excess of the reactants and you kind of minus the products off. Okay, what I'm actually doing, the way I actually kind of remember, or I don't quite remember per se, but if I look at this fusion process, intuitively, I know that this thing will release energy. That's why it's being tried in the tokamak reactors. Okay, tokamaks are basically donuts in Russian. Okay, a lot of the tokamak reactors like ITER, they have a strong magnetic field and they confine plasma in the center. They're trying to achieve this reaction right here and achieve it such that it releases sufficient energy for production. Okay, and there's lots of research going on. So that is what they say their aim is. Okay, so I know this is supposed to release energy. So the Q value is positive. That's an exothermic reaction. Okay, Q value is positive for exothermic. What's exothermic? If you have not heard of this term before, exo means outside. Thermic is thermal heat. So it gives heat to the outside. Okay, gives heat to the outside. Okay, so gives heat to the outside. So Q value is positive for exothermic reactions. So we know fusion, in this case, the fusion of two light nuclei into helium, that is exothermic. So Q value will be positive. So based on this, I will just take the mass excess of the reactants and I minus the product because I know that just by looking at these numbers, they will give me a positive number. Okay, so let me finish this. 2.425 plus 8.071. And I will just quickly use LibreOffice calculator here. Okay, I'm going to open a new one. So you can use this in a calculator or anything else. Okay, so 13.136. Okay, 14.950. Okay, those are the reactants. Deuterium, tritium, and then helium, okay, 4. Okay, normally in nuclear engineering, we like to put the number of nucleons. We want to put it next to the name so that we know what isotope it is. Isotope meaning to say it has the same number of protons, it's the same element, but different number of neutrons. So we want to be quite specific here. Okay, so deuterium is actually hydrogen 2, tritium is hydrogen 3. But deuterium and tritium are the more common names we use for them. Okay, 2.425 here, helium 4, and the neutron is 8.071. Okay, so we have a Q value of the fusion reaction here. Okay, it will be the sum of this minus sum of the products. Okay, 17.59. Okay, so every time the reaction happens, 17.59 MeV comes out. Okay, so that's the Q value of the fusion reaction. Okay, this so Q value nothing too different from before. Okay, nothing too different from before. So basically, it's just calculating the energy difference between the reactants and the products. In this case, I used mass excess. Of course, if you wanted to go the long way round, you could, okay, because we actually did the, we actually tried to do the binding energy, okay. You can do the binding energy way as well, meaning to say, if let's say you have your deuterium, you have your tritium, and then we have our helium plus the neutron, okay, you can sort of calculate the binding energy of these nucleons individually, the total binding energy. So 1, 2, 3, 4, 5. So these are the individual protons and neutrons. You bind them into the helium, you bind them into deuterium and tritium. Okay, and then you calculate the binding energy here. And then here, instead you bind them into helium. So you calculate the binding energy of, in this case, just helium because this is not bound at all. Okay, and then you take the difference between these two binding energies. You will also get the Q value. Okay, so whichever is more convenient, you can use that. Okay, if you have the masses of each individual proton, each individual nucleus, you can actually even do the E equals mc squared version. So you take the mass of the reactants minus the mass of the products because you expect this side to be lighter. Okay, because the more tightly bound it is, the more energy is released, therefore the lighter it is. A equals mc squared. Okay, so if you bind something tighter, it will be lighter. That's the rule of thumb here. Okay, the tighter bound nuclei equals lighter. Okay, for the same number of protons and neutrons. Okay, so anyway, so you calculate the difference between the binding energy of this and this, and you take the heavier stuff, which is here, because this, you know, is an exothermic reaction. And then, so you take the mass of the reactants minus mass of products, then you times C square. So this is the formula here. Mass of reactants, okay, minus mass of products. Okay, so this way you kind of find the change in mass, delta M, change in mass, then you just times the speed of light square, and then you get energy equals mc squared. Okay, and this energy in this case happens to be the Q value. Okay, that's all. I'll see you guys next time. Thanks for watching.